All right, we're just trying to, I'm going to record this one as well, so I just need to get this situated here. Oop. That's not going to work. Hang on. All right. So if you haven't already noticed, most of the teaching that I do is in the public health program. I mostly teach graduate students at the veterinary college, biology students. So for those of you who are in math, we're going to talk more about math in the next little bit. So I'm just going to get... All right. So, you know, we talked about simple models. Oh, that's very annoying to have to look at that. We've talked about simple models, and the problem set that we're going to do at 11 o'clock is really going to help you to start thinking about that simple model lecture as a starting point. So, you know, thinking about how to get some code in R, how to structure the models so that you can run the equations, how you can get the data output, how you can investigate different things. So that's really going to be the function of that first problem set, which I think hopefully should get everybody on the same page. For some of you, it might be a little simplistic. For others, it might be a really good starting point. So the goal is to really make sure that when you go into your project groups, everybody has at least some code that they can use straight out of the gate to really jumpstart your projects. So we've talked a little bit about how host heterogeneity is important here, right? We've talked about the fact that models use a lot of simplifying assumptions, and that many of those simplifying assumptions are things that in reality we know don't really represent the way the world works. And so today in this lecture and then the first lecture tomorrow, we're going to kind of talk about heterogeneity in two pieces. Really, the goal here is to figure out how to structure your model to incorporate variability in different ways. And to be honest, I really feel like listening to me talk at you for all of this time is very painful. So what we're going to do, so I have two host heterogeneity lectures, but what we're going to do is I'm going to do a lecture now to kind of start us off. And then there is a lecture slot tomorrow morning, but really we're going to use it as a hands-on exercise sort of period, where what we'll do is we'll take what we've learned here and we're going to figure out how to get that heterogeneity into R, because that might also be something that you want to think about for your project moving forward. And that way you'll have, again, some initial starting code that will allow you to kind of get into your projects and make sure that anybody who doesn't have a lot of experience with R has some time to feel familiar with it. All right, so we talked a little bit about the force of infection before, right? About the way that force of infection can be denoted as this lambda, and that it's really the rate at which susceptible individuals acquire the infection, or the rate at which they kind of get converted into infected individuals. And so in the way we've been talking about it up until now, this is really proportional to that beta term, right, which is transmission. So again, we're just reviewing here that when we think about a beta for a randomly mixing population, so, you know, if we were all in this room and nobody could enter and nobody could leave and everybody was just like randomly bouncing around, mixing together, beta is the probability of an effective contact. Remember, effective contact is going to depend on how your pathogen is transmitted, right? If the pathogen was transmitted by a tick and we were all in this room, then, you know, we could be randomly mixing and never encounter or have an effective contact that would be sufficient for transmission between two specific individuals. So here, you'll recognize that basically I've just reorganized that R0 equation, right? In the previous lecture, we said R0 is equal to beta, which is probability of transmission, times the contact rate, times the duration of infection. So we're just kind of reorganizing this here. But really, you will sometimes in the modeling literature see this just parameterized as lambda or as the force of infection. And really what they're doing is they're just simplifying, right? They're taking this stuff and they're just grouping it all together and calling it lambda. So, you know, when we think about beta, the way we get to this beta equation is really all we're doing is we're saying, okay, transmission is beta times the susceptibles times the infecteds at any given time point, which is equal to lambda times the susceptibles. And so really we're just, again, rearranging the equation, right? So this is just showing you that we can isolate beta, which is going to be equal to lambda over I. So let's think about, you know, a real world example. And one of the real world examples is age specific differences in force of infection, right? So for some infections, the force of infection is higher in children than in adults. So what are some possible reasons for that observation? Can anybody think of, like, why might you observe a higher force of infection in kids than in adults? Yeah.
Low immunity.
Low immunity. So for instance, it might be that in a specific age group, they are all susceptible to the infection because they are younger, they're newer, they've had less exposure to pathogens, sure. Especially when we think about, you know, when babies are born, oftentimes they will have kind of this period of transient maternal immunity that gets passed down from the mother, which doesn't last that long, right? Then we use infant vaccination and childhood vaccination to help boost their immunity against different pathogens. But so susceptibility, right? We assume that younger individuals potentially have not been exposed to some of these pathogens and they're at higher risk. That's one possible example. What else? Yeah.
Could it be that children are more likely to have checkups or like doctor's appointments out of caution than adults?
So that is probably true because kids do have more contact with the healthcare system by virtue of the fact that they have these kind of standard checkups that are kind of part of that well child. But that doesn't really speak to the force of infection. Why do little kids get sicker more often? Yeah.
Probably have a higher contact rate just because of the behavior of being close and touching their face and mouth with each other.
Yeah, for sure, right? Behaviorally, kids interact in ways that are very different than adults. Both in terms of kind of like their day-to-day behavior, we force them to behave in ways that means they have high numbers of contacts because they go to daycare. They go to kind of congregate settings where they have lots of contact with other little kids. And what else about little kids? They're also not very good at what? Pardon me? Hygiene. They're not great at hygiene, right? So you have kind of the perfect storm, right? So all of these are potential explanations for why kids get sick more often, why they have a higher force of infection. So it could be age-dependent mixing patterns, which we heard somebody say, right? Children are likely to mix with other children rather than adults because of those, you know, daycare, high density, lots of other kids. And they're also more likely to be infectious because they don't have great hygiene. One other possible explanation, right? We're kind of generating hypotheses, right? Possible explanations for why you might observe this. One might be age-dependent differences in susceptibility, right? Which we also heard. Kids might be more susceptible to some of these infections than adults because they haven't been previously exposed. Or you could have some other sort of difference in susceptibility or exposure where, you know, the most susceptible individuals to infection are infected at a young age. So there are lots of possible explanations, right? So I want you to look at this diagram for a second, and I want you to think about, so these are two different populations. So in population A, we have, you know, 0 to 4-year-olds, 5 to 14, and then 15 plus. And let's assume that these are the contacts that they have, right? So here, little kids don't have a ton of contacts. In population B, they have a lot of contacts, and then it's kind of flipped for like older kids in the middle population. Which population do you think it will be easier to control transmission in using infant vaccination? So if you wanted to control disease transmission and you wanted to do it using like infant vaccination, which population do you think it would be best to do? Yep.
Possibly because the younger children may not, they're probably not in school years yet, so they're not going to be in contact with each other as much, and the older children will be, and they have a lower turn-off value there.
Yeah, so one possible, so you might look at this and say, okay, well, these guys have a lot of contact, and so maybe we should do infant vaccination here, because then it prevents, you know, infections from happening in those older groups. Does anybody have a different perspective? Yep.
Question, are we assuming that once they're vaccinated, they can't get?
Let's assume that once they're vaccinated, they can't get sick. Yeah.
I guess I would argue that maybe because like 5 to 14 is like the prime age where kids like mingle, interact. So if they're already vaccinated way back then there's no chance for them to get sick, and there's no chance for them to like transmit the disease because they can't get sick anymore.
Yeah, so okay, so the alternative that I'm hearing is that if you did infant vaccination in a population like A, where you vaccinate them when they're 0 to 4 and they don't have a ton of contacts here, you are kind of being proactive. So like clarify if I am summarizing incorrectly, let me know. So what it sounds like you're saying is that if you do it here, you are kind of being proactive to get them to be immune before they get here where they go to school and then have a ton of contacts. Is that what you're saying? Right. So I would probably argue, for me, I would argue that that is probably the preferred strategy. And it's tricky, right? Because here it looks like, well, they're having a lot of contact, right? But we don't, what this doesn't tell us is it doesn't tell us who the contact is with, right? And so we probably just assumed these were contacts within the age group, but it might not be, right? 0 to 4-year-olds probably have a lot of contact with other adults, and then 5 to 14-year-olds have a lot of school-based contacts, probably maybe more so than 0 to 4 years. Depends, right? There's a lot of variability. Some kids are in daycare, some kids are not. But the point being that really we have to think about not only contact within the group, but we have to think about risk of infection that comes from the other age groups. And that's really what we're going to talk about today. So one of the things we want to think about is how do we incorporate that heterogeneous mixing, right? Mixing within an age group and mixing between the age groups. So really what we're thinking about is a population where the mixing pattern differs between children and adults. And what I want you to think about as we walk through some of these examples is that we're going to talk about kind of young individuals and older individuals. But literally it could be any group that you would like. You might have a pathogen where you say, well, you know, I want to split it based on sex. I want it to be, you know, male, female. Those are the groups. Maybe you want to mix it, you know, split the group or the population based on some other characteristic that you believe to be important. You could break it down by, you know, you might have data that says, well, you know, there's a group of individuals who we would consider to be higher risk and a group of individuals who we would consider to be lower risk for some reason. You could split it that way. So just while we're talking through these examples, I just want you to remember that we're going to talk about young and old, but really the same thing applies to however you want to split this up. So really the force of infection experienced by children, what we're going to call the young group at a given point in time, is given by the sum of the force of infection that we can attribute to contact with other children. And this is going to be the notation you're going to see throughout. Okay, so it's lambda, so the force of infection, and then it has subscripts. So the subscripts tell us where the contact is happening. So if I have YY, this means the force of infection attributable, so the force of infection in young individuals attributable to contact with other young individuals. Whereas if you see this notation, it's the force of infection in young individuals, so the first subscript is in young individuals, as a result of contact with older individuals. So throughout the examples, you will see those subscripts, and it is telling you who's having contact with whom, basically. So really what we're going to do is we are going to stratify our model according to betas or subgroups. So we're going to say these different groups have different forces of infection. So what this tells us is that if we want to know what the overall force of infection in kids or young individuals is, it's going to be the sum of those two things, right? It's going to be the sum of the force of infection that acts on them from having contact with other kids, plus the force of infection that acts on their age group because of contact with older individuals in the population. And you can see here that if we want to think about the force of infection in the older age group, we have the same notation, but here the first subscript is old, so that tells us who it's acting on and where it's coming from as the second subscript, okay? So it's the sum of those two things. So what we can do is we can derive the expression for the force of infection in those younger individuals due to contact with other children. So if we want to think about this force of infection in young kids from other young kids, and really what we're saying is we're just figuring out how do we, like, what is the expression for this, right? And so this is kind of showing you that we have the force of infection times the susceptible kids that are available in the model. And we know that we have this beta, this is the same as, right, lambda is the same as this beta YY times S times I. And so we're just making them equal. So this tells us that lambda is equal to the beta in young kids from other young kids times the number of infected kids who they have contact with. So this is really just kind of showing you where the equation comes from, okay? And then we can derive the exact same expression for the force of infection in young individuals as a result of contact with older individuals. The key thing here is that it depends on how many infecteds there are in each of the groups, right, at any given time. Okay, so really what we're going to do here is that if you, and for some of you who haven't taken math in a long time, this is like we're just substituting in, right? So if we want to find the full force of infection in young individuals, which we talked about as being the sum of these two pieces, and we know that we have an equation for each of these, which is the betas times the number of infecteds in each of the group, then we can come up with this. We can substitute in, right? We're substituting in the beta here instead of the lambda, and so we just are going to add these together. So that's really the logic. That's the logic for how we derive these relationships. So this is for the kids, and here we have the exact same thing, but you can see because the subscripts have changed, these are the equations for the older individuals. Now, some of you may have not looked at matrices in quite a while. So we're going to have a side note to just have a quick review about matrices so that, you know, the math students are like, yes, I know what a matrix is. All right, so it's not that bad. I teach public health students, see in brackets. It's not that bad. Okay, so don't be scared. This is what we're going to do, right? So this is going to look familiar. Hopefully this is going to look vaguely familiar to you from a math class you've taken. So if you have this equation, 5x plus 3y equals 6, and you have this other equation, if we're going to translate it into a matrix, right, what we end up with is we have the 5 from here, the 3 from here, the 3 from here, the 4 from there. We have the x and the y as the unknowns, and then we have what they're equal to, 6 and 3, right? So we're basically taking those equations and we're converting them. We can do it for many equations, right? You could have 2 equations, you could have 3 equations. This is just a little refresher because we're going to do this, but now we're going to do it with the betas and the force of infection and the lambdas and all of the other stuff. So we're going to extend that logic to these force of infection equations. So now we have these force of infection equations, and we're going to basically translate those into a matrix, which gives us this, right? So we have, this is what it's equal to, the force of infection in the young age group, force of infection in the older age group, and then you have this matrix of betas, right? So we have a beta for young individuals from other young individuals. We have a beta for young individuals from the older individuals. We have a beta for the older individuals to the younger individuals, and a beta from old to old. I keep saying old, but I mean, we could differentiate them. However, I mean, you know, old is subjective. And that these are relying on also knowing how many infecteds there are in each of the age groups. Okay, so this is known, you might have seen this called a beta matrix, where we have this group of betas for the different compartments or the different groups in our model. You might also hear it called or you might have read it spelled WAIFW matrix. So who acquires infection from whom matrix, which comes from Anderson and May in 1991. There can be other notations that people use sometimes, but in general, all of this is to say that if we want to incorporate heterogeneity and we want to have different groups, and we want to think about transmission between those different groups, we have to have a matrix that describes the relationships between those groups. So how do we get from here to actually incorporating this into a model, right? So the values for the betas could be calculated, right? So for some examples, you might be able to go to a public health data set where they have like age-specific seroprevalence, for instance. And if you had data on age-specific seroprevalence, you could kind of back into estimates of what those betas are. And you could probably go to the notifiable disease data and figure out, you know, how many infectious individuals are in each age group. But there is a hitch when we think about it. Like in theory, that works, but there's a bit of a hitch. And the hitch is that we have kind of this confusing thing that happens because if we assume the probability that a child contacts and transmits their pathogen to an adult is the same as the probability that an adult contacts and transmits to a child, right? So if you have a contact that occurs, they have to be symmetrical, right? Because it doesn't really work if you say, well, you know, a child has this amount of contact with adults, then you kind of have to assume that the adults have the same amount of contact with the kids. Otherwise, it doesn't really make sense, right? So basically what we're saying is that the beta in old individuals from young, we're going to simplify and say, well, it has to be the same as the reverse. And we're going to call that beta 1. So I'm just going to substitute into the beta and say, okay, so this will be beta 1 and this will be beta 1 to say these are going to be the same because they have to be reciprocal. They have to be even. But we have this like little mathematical problem that we end up with, which is that we have a matrix equation with 2 equations and 3 unknowns, right? So now we say, okay, well, we know what this is, or we're trying to figure out what this is. We know what these are. We have these betas, but we have this. So we have 1, 2, 3 different betas. So what are our options? So we could think about other constraints. And again, this is where you have to really think about your population of interest. You have to know something about the way you think your system works. So if this is our original beta matrix, we could make a simplification where we say, okay, well, we're going to make these 3 betas the same, because ultimately we need to have 2. We can only have 2. So we could simplify and say, well, let's assume that an adult, the probability that an adult contacts and infects a child is the same as the probability that an adult contacts and infects an adult. So we're going to say the main difference here is kids to kids, and everybody else is the same. Or over here, we could make an assumption where we say, you know, adult to adult is significantly different, and all of these 3 are going to be the same. Right? There's really no simple solution to this problem, but it's just to say we have to make some assumptions about what we want the matrix to look like in terms of the structure. So let's think through an example of how we calculate this. So where am I? So let's imagine that we have a population, and we're going to think about rubella, which is a childhood. Yeah.
I have a question.
Yeah. Yes. So really, it's just to simplify the calculations. So we're going to walk through some examples, and then I think you'll see why it's important that we simplify it down to 2. Now, in reality, right, you know, we make models all the time that have lots of different age groups that describe very complicated contact patterns between all of those different age groups, but all of that is really rooted in this kind of basic premise. And so we're kind of starting at grassroots here, but you're exactly right, that, you know, we could extend this to many, many different groups, but still we kind of have to think about how we're going to parameterize those betas. Yep. Yes. Yeah. No, it's going to be a rate per time. Yep.
So the assumption is not always true, right? So you are, can you give me an example that the assumption fails?
An example where the assumption, so like in terms of these assumptions?
No, like the last line.
Last slide. All right. Here?
Yeah. So assuming the probability of young to old equals to the probability of old to young.
Yeah.
And when is that the case? This fails.
Well, it's not really that the assumption fails. So the issue is that if we have the matrix and we're saying that the matrix, so we're saying, you know, let's think about it in terms of contacts, right? Just contact rate. So if we say the average child has 5 adult contacts per day, and we collect that information and we say, yes, the average child has an average of 5 adult contacts per day, then it would make sense that if that was the case, then if we asked adults how many contacts they had with children, you know, they shouldn't report, we have 100 contacts with children each day, right? So the issue is just, we assume that they must be similar, right? Does that make sense? So you know, we can't say, well, you know, if kids have 5 contacts per day, it wouldn't make sense that adults have like 100 contacts per day with kids. So we're just simplifying and saying that they're the same, right? The contact that occurs between kids and adults is going to be the same as adults with kids. This is just a simplifying assumption we're making here. Like, So what you're asking is, are there examples where that doesn't work, right? I mean, sure, you could think of examples where, you know, you might say, well, but really we're talking about averages here, right? So, you know, you might say, well, some people maybe have a job, for instance. So here's an example, right? If you're a preschool teacher and you're an adult and I ask you how many contacts you have with little kids, you might say, oh, I have tons. I have 50 a day. But that's not the, you know, like that's a very specific occupation that has that amount of contact. And, you know, actually, I'm going to come back to that because at the end of my talk today, we're going to talk a little bit about some research we've done related to contacts over the pandemic. And we'll come back to that because there are some interesting things that we find there that kind of talk about this, about variability between the different groups. Okay. Exactly. So we also have to think about what is a contact, right? So you're exactly right, is that, you know, when we start making the models, they start to get really complicated because then you have to take into account, you're right, vaccine status might be important, right? Because if I am vaccinated with a, you know, sterilizing vaccine, it might not really matter if I have 100 contacts with people because I am not going to become infected, right? So you're right, the effective contact piece is important for us to think about. So this is kind of just the theory. So now we're going to talk about like how this works in the real world, right? So let's imagine that we have rubella in a population. And we have these numbers, right? So 0.12 and 0.05 per year for individuals under and over 15 years, right? So force of infection in individuals less than 15 is higher than individuals older than 15 in this example. And we're going to assume that in this population, the age-specific force of infection values result in 29 and 6 infectious cases among children and adults. So if we take this information and we plop it into our matrix, we have 29, that was the number of infected kids, and 6, that was the number of infected adults. We have the force of infection that we could estimate from, let's say, seroprevalence surveys, 0.12, 0.05, and then we have this beta matrix. So let's assume a totally unrealistic who acquires infection from whom matrix for a start because it's easy, right? So what does this structure, if we look at the matrix here, what does this structure imply? If I zero out some of those betas, what does that say about the biology in this specific system? Yep.
It's very homogeneous and there's no.
Exactly. What this tells us is that there's no transmission between the age groups. We're saying kids only get rubella from other kids, adults only get rubella from other adults, and the beta here is 0 and the beta here is 0. No transmission between the age groups. So this is totally unrealistic, but we could do that. If we make these 0, then we have 2 unknowns, and we can solve for the betas, right? So we can use what we have from the seroprevalence study, from the notifiable diseases data, and we can solve for beta to tell us what the betas would be in this instance. So the beta 1 here is higher than the beta 2. So this tells us that the beta in kids is going to be higher than the beta in adults, which makes sense because we have way more infections in kids and a much higher seroprevalence or force of infection in kids, right? But this is not realistic. This doesn't really make any sense because we know that that's not how rubella is transmitted. So let's assume a more realistic matrix. So what does this matrix imply? So we've made a simplifying assumption, certainly. So we still have a simplifying assumption here, but what does this assume?
Probability of young to old and old to young is to the old to old.
Exactly. So in this case, we're saying these 3 betas are going to be the same. These are all equivalent, and the major difference is transmission from young to young. So we have 1 beta to represent this transmission, and then we have this beta. We're going to say these are all the same. So again, we can solve for the beta terms. right? We can take the matrix and we can just write out the equations, and then we can solve for beta. So this is just step by step, and I write it out like this, that when you go back in your notes, you can figure out how to actually, how we got to the betas. But what you can see is that in this example, the beta is 0.0038 per year. And then you could solve for, so, and then we have the beta 2 up here, which is 0.0014. So, in a randomly mixing population, the expected proportion of susceptibles in the different age groups, assuming the force of infection is not age dependent, can be written as this. And the overall number of susceptible individuals can be found by summing up the average number of susceptibles in each of the age groups. Again, this is not something that we're going to you're not going to need to know this per se, but it just talks about the fact that we also have to think about the proportion of the population that is susceptible. And then we see that the average number of infectious individuals in the population is given by, again, the number of newly infected individuals times the duration of infectiousness. And again, this is just kind of walking through the logic, right? How we get there in terms of the relationships. But we have this other issue where when we have a non-randomly mixing population, we need to extend that logic into these different age groups. So we need estimates of the average number of young and old infectious individuals. So it could be, if we want to talk about young individuals, the lambda in the young times the susceptible youngs times the duration of infection. And we also have it for the older individuals as well. So again, this is just walking through kind of where the values are coming from. And again, this talks to the point that we also have in a homogeneously mixing population, right? We have the R0, which assumes the whole population is susceptible, but then we have the effective reproductive number. So the effective reproductive number is the R0 times the proportion of the population that's susceptible, right? So as we start to have some immunity in the population, we're not really talking about a basic reproductive number at that point because some individuals are immune. We're now talking about an effective reproductive number. So we know that there's this relationship between R0 and the proportion of the population susceptible. And we have this herd immunity threshold, which we talked about when we talked about how much vaccine coverage you would need based on the different reproductive numbers. The problem is that all of these relationships that we talked about don't apply in the same way as soon as we start assuming that mixing is no longer random, right? If we want to estimate the reproductive number for a heterogeneously mixing population, we need to go through a few different steps. We need to figure out what the prevalence of infection in the population is. We could do that using a serosurvey. We could estimate the force of infection. We could choose the structure of that beta matrix. Then we can calculate the transmission coefficients or those betas. So all of these things we've talked about up until now, right, step by step. And then we formulate this next generation matrix and then calculate R0 from there. In a population with heterogeneous mixing, where you have different groups that mix in different amounts, the number of secondary cases that come from an infected case is going to depend on which subgroup the infected individual comes from. So each of these reproductive numbers are expressed in terms of the coefficients from the matrix. So you're going to see that in a minute. So this is what we saw in the first lecture, right? In a homogeneously mixed population where we have a basic reproductive number, beta times N times D. In a heterogeneously mixed population, we now have 4 different relationships, right? Because we have the reproductive number in young individuals from other young individuals, in older individuals from young individuals. So we have one for each of those groups that we talked about, and it relies on the beta, right? The beta that we calculated in the matrix. And then we end up with this matrix that looks like this. So we have the betas on one side and we have the R's on the other, with the number of secondary cases resulting from the introduction of an infected case into the population is some average of these R values. So let's walk through a couple of examples, because I always find like you talk about it, but then if you don't actually work through the examples, it kind of comes together when you start thinking about the examples. So let's assume that we have, so up here in the corner, this is just to remind you of what the matrix is, right? It reminds you of what the subscripts are so that you can keep track. So in a population with a matrix like this, 1, 1, 1, 1, an infectious case in either of the subgroups causes one secondary infection in its own subgroup, right? So this is young, young. One secondary case in its own subgroup, and one secondary case in the other subgroup, and therefore leads to 2 secondary cases. So the basic reproductive number in the population is therefore 2. So if we looked at something like this, right, again, look at our little reminder up there with the subscripts about which number goes with which group. In this example, you have more secondary cases in the within subgroup than the between subgroups. So what I wanted to kind of wrap up with as we head into kind of like the first problem set is to talk about a real example of this, because I think, you know, we've kind of like distilled this down into like the basic groups. But one of the things that you have probably seen, and what we're going to work through tomorrow in the hands-on exercise, is thinking about a much more complicated who acquires infection from whom matrix. And the really nice thing about R is that a lot of these data are already in a package in R called Social Mixer. And so you can kind of pull those data in and then use them in different ways. So one of the things we did during the early stages of the pandemic was we had this mathematical model of the Canadian population. But if we want to talk about transmission of SARS-CoV-2 in Canada, we can't have a model that has like young individuals and old individuals, right? I can't have a 2-compartment model. It doesn't work. And it doesn't work for a bunch of reasons. Number one is because we knew that the risk, depending on age, was like very different. So you had to be able to keep the age groups broken out quite significantly. And so one of the things that you will see written about in the literature is something called Mossam et al., which is kind of one of the very early contact matrix studies, where they show the amount of contact between individuals of different ages. And there's subsequently another paper by Prem et al., which does a similar sort of thing. This is for Great Britain. The Mossam et al. Study was done where basically they did a contact diary study. So they went out to people who lived in Great Britain and they said, would you like to participate in our study? Here is like a paper diary, and we want you to record how many contacts you have with individuals every day and estimate like what age they are, right? And so people agreed to do this, and adults completed the surveys for their kids also, so they like estimated kid contacts. And in the end, they did it for, I think, 7 or 8 countries. I can't remember off the top, 8 maybe. And you get a very similar, it actually doesn't matter what country of data you look at, they all look almost identical. And what it tells us is that, again, like we talked about in the beginning, you know, young individuals, basically on the diagonal here, have the most contact within their age group, right? So 20-year-olds have the most contact with other 20-year-olds on average over the course of a day. Little kids have lots of contact with other little kids. And you see that little kids also have a lot of contact with people in this age range, which makes sense because little kids can't live alone. They have to have contact with adults in some way. And same thing here, right? These individuals have contact with little kids. And you have little kids have far less contact with people at the very oldest age group on average in a single day. So we have these matrices, and this is represented as a heat map, but you can actually break these matrices down by lots of different age groups. groups. You can say, you know, what sort of age groups do you want? And you can kind of reorganize this in a way that allows you to kind of understand what's happening in terms of contact between the different age groups. So we developed this model early in the pandemic, and we used these data, right? They're not Canadian data, but you know, the 8 studies they had done across all the different countries, I mean, not dramatically different. So we figure it's close enough. And so we developed these age structured models, and you know, the age structured model says this is not great, especially early on in the pandemic. You know, if you don't do anything, you're going to have lots and lots of cases, and you're going to have, you know, basically a curve that like goes way over the hospital capacity. It's actually so bad that you can't actually see what's happening here, so you have to like drop, like squish the y-axis to just see the top, because the peak in the do nothing case is so bad. And then basically what the model said was, you know, if you want to keep transmission low in order to preserve ICU capacity, you basically are going to have to like dial up and down the public health measures we have available to us, which early in the pandemic were not vaccine. They were not, you know, pharmaceutical interventions. They were, you know, the hammer type interventions, which is physical distancing, which, you know, so enhanced case detection by ramping up testing so you can find cases, all of that sort of stuff. And what the model said was, you know, in these early days of the pandemic, really, we have to protect hospital capacity. The way we do that is by basically, you know, ramping up these non-pharmaceutical interventions. And, you know, as soon as you let them off, the cases will start to come back up, and then you'll have to re-implement them until we can limp our way to a vaccine. And this was like, you know, people didn't like this. I mean, this was like, I don't remember what, March 2020. People really didn't like this. They didn't like that the model said this is going to go on for a long time until we have, you know, vaccine, and until we have, you know, a better plan for what we're going to do here. And then what we did, so we used those contact matrices, and then what we did was so if you imagine the contact matrices that we talked about, right, where you have contact between the different age groups, within the age groups, and between the age groups, we want to model social distancing. So how do you think you could model, if you think about the contact matrix that we've talked about this morning, in a very simplistic way, what would you do if you wanted to incorporate social distancing, which acts on contacts? It's an intervention to reduce contact. What could you do in a model in a very simple way? It's not a trick question. Yeah.
Like just reducing the contact.
Just reduce the contact, exactly. So you have a contact matrix, and then you could say, well, what happens if we just like dial it down a little bit? Like how much would you have to dial it down? Like how much less contact would you need to have? And so what we did was we then modeled relaxation of physical distancing. So basically we implemented in the model, so in the model we started by just saying, okay, like let's use the hammer and just like, you know, really bang the contact rate down a lot, like 70% reduction. Then the question is, you know, what happens as you relax the physical distancing? So early in the pandemic, we really squished the contact rate down, but then we're going to relax it. And one of the questions was like, how much could you relax it before you would start to see resurgence of cases? And it turns out that, you know, the issue in Ontario is that we were relaxing. The government really wanted to relax physical distancing, but we still had a lot of transmission. And we still had no vaccine, and we still had the hospitals being very, very overcrowded. And so here you can see reduction in contacts relative to normal is that basically if you just return to normal, so if you relax the physical distancing and you just allow the contact matrix to go back to normal, you get this solid line. It takes 41 days until you swamp out the hospitals a second time if you just allow everything to go back to normal. And then we said, well, you know, let's dial them down and modify those contact rates a little bit differently. What happens if we have a 10% reduction, a 30% reduction, a 50% reduction? And it looked like, you could relax a little bit, but you couldn't go back to normal. Going back, just relaxing physical distancing and allowing the contacts to fully go back to normal was just not going to be a reasonable plan if you wanted to avoid individuals becoming infected. And so, I'm not sure why it's like that. One of the things, so we had this model, and one of the questions, yep.
Yeah, so
Yeah, you're exactly right. So what we assume is that those, so we parameterize it using those Masson et al. Contact matrices or the PREM contact matrices. And those were data that were collected not during a pandemic. They were regular, everyday, no public health emergency data. So we assume that represents the normal amount of contact, and then we dial them down. But this raises a good question, right? Because the question is like, what are people actually doing? Because like you have these models and you're saying, well, you have to reduce it by 70%, you have to reduce it by 50%. So one of the things that we did was we had this model. So we had some preliminary data, we parameterized the model. And then one of the things that public health wanted to know is how will we know, right? How will we know whether we are reducing contacts enough to actually keep transmission low? And so what we wanted to do is we said, well, there's really no way to know unless you ask people. You have to collect new data. And so we came back to this data piece and we mounted 4 cross-sectional surveys across Canada where we asked people about perceived effectiveness and confidence in public health measures. And what we actually did was we asked people to complete the exact same template as Masson et al. Used in their study. And so we had this longitudinal data. So we had cross-sectional data where we asked Canadians. And the really interesting thing from the data was that, there was a lot of discussion about the fact that, the government was saying everybody should reduce their contacts. And then when cases continued to go up, the government would have press conferences where they would like point their finger and say, you people are not following the rules. The reason cases are going up is because everybody is not following the rules. And our data, I think this is one of the things that I would argue is really important to like have modelers who interact with people who collect data or people who are involved with data, because our data actually said that was not true. Our data collected across Canada said the vast majority of people who we surveyed in May, July, September, December, all of them reported having very significantly reduced their contact outside of their workplace, because a lot of workplaces were starting to require people to come back in person. So we argued that, it's not general social contacts that are driving, it's not people having parties that are driving transmission. What's driving transmission now is contacts in the workplace. And the fact that people don't have paid sick days, which allows them to not go to work sick. And so, we also did these longitudinal studies. So these were studies that we mounted during the pandemic to actually try to figure out where we were in terms of contacts that we could compare them to the model, which I think is a really useful exercise. And this shows you, so these are our contact matrices from those studies. So this shows you the age of the participants. So in our study, we didn't have kids. We had only people who were over 18 participate in the study. And then we have the age of the contact. And the number in the cell is actually the reduction compared to the normal amount of contact. So you can see that in May 2020, most people had were significantly reducing their contacts. They were having like 70–80% reduction compared to pre-pandemic contact, except for a few up there in the older age groups. July, people still dramatically reducing their contact. And this makes sense. If you actually translate these contact matrices into estimates of the reproductive number, this matrix yields a reproductive number that is below 1. This matrix also yields a reproductive number that is less than 1, which means that, we had pretty good control of transmission at those points in time. what you can see is that in September, the matrix changed dramatically. This was when schools went back and many, many people went back to work. Inevitably, the contacts had to come up. And what we knew was that the contacts from the data we had collected, the contact matrix showed that almost all of the age groups showed reductions that now were going to favor transmission, right? They were not reduced enough to continue to suppress. And this lines up with what we observed. So this matrix here still reduced, but not reduced enough to control transmission. So now the reproductive number starts to cross 1. We start to see growth again. And then by the time we got to December, what do you see in December that's kind of interesting? Because this is really kind of, we thought this was very interesting because December, we weren't like being too proactive in Ontario. Like we were not like trying to do much until about Boxing Day. But there was something that happened in December. So these are just the Ontario, no, maybe these are national contacts. I can't remember. Does anybody have a thought?
Is it more the seniors?
Yeah, for sure. So we start to see some of the older individuals are pulling back, right, on their contacts. So they're reducing their contacts more, probably because they're at high risk of severe outcomes. But a lot of the groups have started climbing back up, right? And when the number goes up, it means their contact is going down. They're reducing their contact a lot. And the interesting thing here is that this is actually before we started implementing new measures to try to reduce transmission. So what this tells us is that people were very aware that the situation was getting worse, and they were proactively changing their behavior, which helped to kind of drive this reproductive number down again. We weren't actively doing much on the public health side, and yet the matrix said, people understand, right? They see the cases going up, they automatically start to change their behavior in response to that. Yep. Yeah, so certainly the cases were increasing here, and what we're doing now is we have a model that's under review right now that kind of takes into account kind of that self-selection, if you want to call it that, where people respond to what they see in the case numbers, not to kind of what the government is telling them to do. But it doesn't hold. So the issue is that, you know, we were going into December here, cases were increasing, people were pulling their contacts back, but does anybody else know what was happening here? Something changed dramatically that really changed the trajectory. Pardon me? Change in variants, right? So then you also have this issue, which is that at a certain point, if you have a new variant come along where transmission is really, really much higher, what do you think has to happen? So like, I mean, if you reduce contacts to suppress transmission for wild type, but then you get a new variant, if the new variant is more transmissible, to keep control, you have to reduce contacts even more, right? And so at a certain point, it became quite tricky to figure out where that balance was. But I think the key thing for us was that in the contact matrix, you could break it out by location, because we also asked people about where the contacts were happening. And so the home contacts, the social contacts really didn't change over the course of the year. Where you start to see the matrix light up is in work-related contacts. And that comes back to my comment about the fact that, you know, wagging our finger at people and telling them not to have social gatherings was really not targeting where the majority of contact was coming from that was leading to these kind of explosive outbreaks that we were seeing, is that it was really being driven, according to our data, by work-related contacts. So a real-world example of kind of moving from that very simple contact matrix to kind of a real-world example where we use that in a model to help us think through interventions for SARS-CoV-2. Yep.
Could you account for the bias in the data for
Yeah, so I mean, it's important, right? So I think there are a number of limitations to these sorts of data, right? So first of all, is that we collected the surveys during a pandemic and we mounted the surveys very rapidly, which meant that we used like a survey company to collect the data. So they have like these panels of people who fill in surveys, which are probably not representative of the average person. But we had a number of colleagues who had used these panels for a bunch of other studies not related to the pandemic, and their data really seemed to suggest that the panels were actually pretty representative, and we selected individuals to weight according to the population, like so all of the samples were weighted by geography, so population density basically by geography and province and territory, age, sex, and so we did feel like it was as representative as we could possibly get it. But it is always going to be the case that when you collect data, there are always going to be biases, right? So, one thing might be people who are staying at home filling in online surveys are probably, many of those people may be working from home already, right? So maybe we're totally underestimating work-related contacts, and work-related contacts were way higher because the people who are going into work are not filling in the survey. The kid contacts, we didn't collect kid contacts, but on the December survey, we asked parents about contacts with kids, like how many contacts their kids had, both in school, whether they had bus-related contacts and whether they had extracurricular-related contacts. And the kid-related contacts reported in December were really high. Like by the time you take into account school class size and bus contacts, plus almost all of the people who had kids in our study reported that their kids had, like tons of extracurricular contacts on top of their school contacts. So like sporting and all arts, all that sort of stuff. So like kids were having like more than 40 contacts a day with other kids and also with adults who were involved in all of those activities. So we talk a little bit about that in the paper, but for sure there's a lot that you need to think about when you collect the data, because it's not going to be a perfect representation, and it is certainly going to be biased towards certain people who are filling in surveys. Yep.
Pandemic, like after the paper, were you able to access like campus data during the pandemic and compare it back to the model?
Yeah, so what we've been that's what we're trying to work on now. So we have kind of that underway, and then we also have the models where we try to incorporate this like individual behavior change, because I think that that's important. So like to try to understand like what was most responsible for reducing cases, like do you need the government hammer, or was it the case that like individual behavior change was enough? And the model seems to suggest that it's not enough, that you can ask people to rely on their individual behaviors, and in our study many people were engaging in proactive behavior change in the contact matrix, but when you put that into a model, it's still not sufficient to really squash transmission down.
Yeah, especially with like the workplace data. I did a lot of patient interviews during as well, and one common thing about the workplace is mostly people were told to come in 3 days post-infection.
Yeah.
And they were like servers.
Yes. Yeah. Exactly. And, and we also had large, like a lot of the workplaces that had really large outbreaks were like, essential services, right? Like, I mean, many people had the privilege to stay home on the backs of people who had to go work at the Amazon warehouse, right? So that we could all order our stuff. And then the people who had to go to the Amazon warehouse all had, COVID and were very ill and transmitted and lots of issues. So yeah, I mean, there is also a huge equity piece to all of this that we haven't talked about that's really important. Okay, so we are going to, let me find my next thing here. So the problem set number 1 is on the website. It's an R Markdown file. And basically what it's going to ask you to do is set up and interpret some very simple compartment models. And like I said before, I've given you all of the starting code so that you at least have a simple model that you can start with. And then I'm going to ask you to modify it in different ways. One of the things that I think we wanted to do is, one of the things that we wanted to do was have you do the problem sets in groups. And so, you know, self-selection typically works, but I do think that, you know, not everybody has the same experience working in R. We have math students, we have public health students, we have biology students, we have, I don't know what else, computer science students, I don't know. We have students from lots of different places. Some of you have already been building models and working on models for your graduate work. Others have never built a model, and this is really your first introduction. So it would be very nice to put together groups that have a mixture of skills, because I think especially for the first problem set, it will allow you to kind of work together so that people bring different skill sets to the table. And it's one of the best ways for students who are not familiar with building models in R to really have some support from the math students to figure out how this actually works. There are spaces, so you know this is not a great group work space in here. Certainly you're welcome to stay in here. There is like a little library lounge next door where there are kind of tables and chairs and you can sit together and work through it. There's also a lab across the way. I think it's like a wet lab, so again, you might have to kind of like rearrange the stools and hold your laptop on your lap or find some way to kind of work together. The problem set is, you know, code, has some questions, has 4 different questions where it's asking you to do different things, interpret different outputs, that sort of stuff. Very simple starting out work. And we'll go from there. The problem sets do get handed in, but you know, this is the problem set for me. I am totally like, it's not really, I don't view this as like independent work. Like I want you to collaborate. I want you to like sit and troubleshoot and work through it together. You're going to be required to submit your own assignment, but I do think that it's helpful for you to kind of like work through it in teams. Is that anything else I need to tell them?
We haven't talked about this, and I'm not sure what the answer should be. Just like, when is the deadline for handing in stuff to be assessed? So I guess on the one hand, like, you want to get the work knocked off so you can keep getting more work done, but on the other hand, it's a pretty intense schedule, and so I think we should maybe talk as instructors about when is the deadline.
Yeah. So we'll figure out what the deadline is not today. How about that? The deadline will not be today, and we will tell you what the deadline is. But I mean, this shouldn't take you that long. Like this is pretty straightforward, not overwhelming. Just start getting your feet wet, sort of.
The deadline was yesterday.
The deadline was yesterday. Exactly. You should have started it before you came. Public health. Just joking. Just like public health. Start getting used to it. The deadline was yesterday. Any questions, comments, concerns? Yes.
You might have answered this while I was in the washroom, but I was looking through the README file or the RD file, and there's some images that you have to reference, and I don't know where those files are supposed to be. They're not rendering up. Obviously, it's obviously in your.
Because normally I had it as a PDF, so normally I share the PDF, and that's the issue. So I send you the markdown and not the PDF. Okay. Can I send Amy the PDF and it will go somewhere where they can
You could
see
probably
it?
even send it to James or Julian, and we'll just, so like, there's quite a lot of stuff linked off the website. And I think earlier James and Julian were like troubleshooting. So for the AARMS-EIDM website, if you go to the courses, Amy's lectures from this morning, like the slides are there. So you go to course 1, mathematical epidemiology, and you scroll down and there's Amy's slides. I guess Greg's already found it. So yeah, like Amy just needs to email
I didn't think about that. I can also put, okay. So the first image is not really that fancy. It's this image. It's like an SEIR picture. You could just scribble it on your piece of paper so you can see what it looks like. I will send the PDFs that it's up there. But the first image, it will say this, SEIR.png. This is all that's supposed to be there. And it's going to ask you some questions about that. What I will say is that not all of this is stuff that you're going to do in Markdown. So, you know, you can do this separately, like even if you just write it out on a piece of paper and then, because I do think that sometimes it's helpful, especially when you're starting out, to like force yourself to write out the equations, like to draw the compartment diagram and to kind of like write it. So like question 1 says, write down the differential equations for the model. You know, you can do that however you want. If you want to literally write it on a piece of paper and then put it back in as a screenshot or whatever, however you want to do it, you can do that. So that's that one. And then I do have kind of this table where I just have some very basic parameter values. Oh yeah, you can take a picture of it. I will still upload the PDF, but if you want to take a picture of it, then you kind of have it immediately. I think those are the only two. They are kind of important, but they're the two main. That will get you started, and then I'll send the PDFs that you have the copy. So find someone in your group who has a photo of it for the time being. Okay, is that all right? Yes? All right, so disperse. We're going to work on it for, at this point, maybe like 45 minutes-ish. I'm going to wander around, so if you have questions or, you know, I'll kind of bounce around from group to group as we go until lunchtime. Sound good? All right, perfect.
Yeah, and just like a range scale, I think. Some people get it hard, some people might need to.
Yeah, maybe. Like that's a good question. How do we? Is there a way to self-identify?
Who's used R before?
Who's used R before? Put your hand up if you've used R before. Like confidently used R. But, some people are like, I don't know. Okay. So. James?
I'm guessing everything can be done in Python.
Oh my God, okay. If you want to do it in Python, you're on your own. Or MATLAB. MATLAB, I mean, you can do it in lots of different things, but I gave you the code in R. Okay.
Yeah, how are we gonna submit it? Are we gonna populate to GitHub or?
Yeah, so I think what's going to happen with the assignments at the end is that they'll be submitted through the MUN Learn LMS. Is it Brightspace? Is that what it's called? Yeah. So the MUN LMS. So you guys would have been set up with student accounts on there. So anything that gets submitted will be submitted through there because of yeah, PDF would work. Yeah. Yeah.
If you have everything on like a Git repo, is sharing that like a more painful integrator than putting it into the thing that you just said?
Amy probably wanted through the MUN.
There's no problem. I just if I'm writing it all there then.
So I've said before, like the Brightspace, I just use it for things where there's a privacy element. So like, you know, maybe everyone doesn't want to make their assignment public. So that would be one reason why I want to use Brightspace. The other thing is it gives a timestamp on it. So if we say like the assignment is due at a certain time. So, I mean, I don't, if you're comfortable sharing your assignment publicly, like I don't really have a huge problem with that. I guess we can also see the history of when the last time you changed it. I just think for whoever's marking it, it might, I don't know if they would find it easier or harder. So if is marking this, I think you'd probably find it easier if you submitted it to Brightspace.
What if are most people on the Slack? What if I just dump the PDF onto the Slack? Does that work for people? That's probably the easiest option.
Well, in some ways it's easier.
With algorithm's done, then you can make
And you don't have to stay in here. If you go to the lounge and just sit in a chair, then people will come sit in the chairs around you, and you can just hope that someone knows how to run R, and you'll be good. Yes.
Yeah, I guess the mic, right, it didn't give you trouble, the microphone.
Yeah.
I hope it went
I think it worked. I will send you, I have to go on and get the, like, pull the files, and sometimes it takes them a while to kind of
to
compile, but I will send it to you as soon as I get it this afternoon. Sound good?
Well, okay, you really don't need to do much. You need to submit your assignments to the and get grade. When it's over, it will take a while. Okay, like whatever you see on Brightspace is not your real grades, right? Like, your real grades are on your transcript. So eventually it will show up on your transcript. I mean, yeah, I don't know if we'll put the final grade on. We can put the final grade on Brightspace, but it was really. Does that make sense? Because so you're supervised. Yeah, so you just need to talk to them and I'll talk to them as well. Afterwards, just, we have to contact them. Yeah, so let's meet after we'll make a plan. If you guys want to.
But I don't know if I'm teaching. Currently, I gave you that has one place for projection there.
Okay.
I'm trying to tell them.
So we'll just, everyone meet.
Because I'm going to film my lectures in real time. If I have whiteboard and blackboard set, it's going to be a mess. Anyway. This makes no sense. Yes.
Taking the photo with your phone.
No, Stephanie said something. Right to get